The title of this presentation is The Emptiness Formation Probability and Non-Local Correlations for the 20 Vertex Model. To begin with a presentation overview, we'll be discussing connections between the 6 vertex model and the 20 vertex models, and it's kind of relating a lot to some other previous presentations that I've given, in which I've really drawn the attention of the viewer to the fact that the quantum inverse scattering framework, which we're going to really describe as, or what is also abbreviated in some papers in the literature as QISM, can really be used for many different types of vertex models, and how it can really help us understand these models together in kind of like an aggregate or a class of models for different types of behaviors that they might exhibit. And as we say in the second bullet point here, we'll be introducing from a very general level previous motivations of the author, me, through investigations of the quantum inverse scattering method. And in doing so, we'll have to introduce objects of the QISM, hence allowing for us to further understand the transfer matrix, the quantum monodromy matrix, along with closely related objects. And we'll first begin by discussing the 6 vertex model. The 6 vertex model is a classical model of statistical mechanics. And like I've talked about in many of my papers on the 6 vertex model and the 20 vertex model, these classes of models or types of models were originally introduced for looking at thermodynamic properties of ice. And this was originally introduced in more of a chemistry context from Pauling when he was a professor at Caltech, in which he was looking at ways to look at configurations of hydrogen and oxygen atoms together in the lattice. And for this particular model that's defined over the square lattice in comparison to the 20 vertex model that I'll introduce, which is defined over the triangular lattice instead for a 3-dimensional version of the 6 vertex model. This vertex model has 6 possible configurations, and it's given by the constraint that you have to have an arrow conservation through an ice rule, which pretty much means that you have to either have 2 arrows pointing in or 2 arrows pointing out at each vertex. And what's associated with the 6 vertex model that makes it different from percolation type models, or maybe the random cluster model or the Potts model, or even the dilute Potts model that I've seen, which Nienhuis characterized through the existence of either macroscopic or microscopic loops, is that there's a height function representation, which is given formally speaking by a graph homomorphism, which is a function, a mapping from the faces of the square lattice or the faces of the triangular lattice, whatever lattice you define your vertex model on, which can then be mapped into the reals, the integers. It can be either a positive or negative integer, which is describing what is the image of the graph homomorphism, and hence what is the image or the value of the height function along this face of the square lattice. And you can see that given in the first configuration that's given here for the 6 vertex model, depending upon whether we traverse an oriented edge that's in between one face of the graph homomorphism and another face of the graph homomorphism, namely the height function, the image or the value of the height function on this face will either increase or decrease by 1. If we traverse an arrow that is going outwards, it decreases by 1, but otherwise, if the arrow was in the reverse, the only other possible orientation for the orientation of this edge about the vertex that we're looking at, the height function would increase by 1, which is shown by the second configuration right next to the first configuration. And obviously within the literature of any type of model that you study, and obviously there's no exception for statistical mechanics, there's a lot of different types of ways to visually represent the configurations of the 6 vertex model or the 20 vertex model, in which the configurations from the sample space that are given for the 6 vertex model in the top part of the slide are called arrow configurations. But while the configurations that are given in the bottom for the 6 vertex model are instead line configurations, which is just denoted by either shading some line either black or white, depending upon the orientation of the edges that are in bijection with the orientation of the arrows from the 6 vertex configurations from the arrow sample space. And explicitly, we can define the probability measure for the 6 vertex model by a probability measure that's supported over the torus. But obviously, the torus isn't the only type of environment that you can look to define a 6 vertex probability measure over, because even like in a lot of other papers from Duminel Copan and his colleagues, from people who work in his group and closely related, they look at the 6 vertex model probability measure supported over the cylinder, strips of the square lattice, So there are a variety of environments that you can define this probability measure as being supported over. But the fact is that it's helpful for us to look at the torus because in that case, you really have some type of issue sometimes when you're mapping the height function from one boundary to another, because it's given by the fact that as a result of the torus being defined as a periodic embedding of the square lattice, you could have a problem and an issue of gluing boundary conditions of the height function when you're wrapping around the torus, which could lead to what is called a multi-valued height function. And we really sidestep this difficulty by just defining the boundaries in such a way so that there's only one value of the height function that can be defined when you're wrapping values around the torus. But explicitly, the probability measure for the six vertex model under domain wall boundary conditions, which is the types of boundary conditions that there are also a counterpart of on the pentagonal lattice or the triangular lattice for the 20 vertex model, is given by a ratio of the weight function normalized by the partition function under boundary condition C, namely under domain wall boundary conditions, that's also supported over the torus. And the weight function, which is appearing in the numerator of the probability measure for the six vertex model, that's normalized by the partition function, takes the weight of A1 to the N1, A2 to the N2, B1 to the N3, and so on for parameters B2, C1, and C2. And in this expression for the weight function, that's not given by an isotropic parameter choice, A1, A2, B1, B2, C1, and C2 are all strictly positive, and all of the exponents N1 through N6, which are used on each one of the factors in the weight function for the six vertex model, is given by the number of arrows pointing for each vertex of type 1 all the way up to type 6. And the partition function that's normalizing the probability measure so that the expression for the probability measure is in fact a probability measure for the six vertex model is given by just a summation over the sample space supported over the torus of all of the weights of all possible configurations appearing in the sample space. And as I had alluded to in the previous slide, under an isotropic parameter choice, you can establish a correspondence between setting A1 equal to A2 equal to A, or B1 equal to B2 equal to B, or even C1 equal to C2 equal to C, which can give a way to homogenize the types of weights which appear in the weight function of the six vertex model, which can be a little more simple for studying the resulting probability measure. But we can also introduce an alternative parameterization of weights. In this parameterization of weights that first appeared for the six vertex model, it was showing up more in a paper from Keating, Reshetikhin, and Sridhar that I studied in in a paper first, I think like October or November last year, in which I was pretty much looking to answer one of their questions about integrability of a Hamiltonian flow for the six vertex model. And in the sense of integrability, in the context of integrability, you can introduce a different types of parameterization for the weights of the six vertex model rather than the isotropic parameter choice for all the weights that I gave in the previous slide, which is given in the presence of two external fields H and V. And you can pretty much take an exponential to H plus V minus H minus V, H minus V minus H plus V, as well as using some auxiliary parameter lambda, which is taken to be greater than or equal to 1 for the last weights C1 and C2. So this is to say that it really depends on what types of parameter choices you want to use and whether you want to simplify or restrict the total number of possible weights that you can have for your six vertex weight function, and hence, which also impacts the structure of the probability measure, which would then determine which types of characteristics of the model you want to study, because the six vertex model and the 20 vertex models, they're very rich models in that there's a lot of behaviors that people would like to study, whether it be ranging from crossing probability estimates or Russell-Seymour-Welsh, or even integrability, like I've been trying to do in some of my works more recently over the past several months. And like we had alluded to in previous works of the author, integrability of the six vertex model was established with several computations using the Poisson bracket. And the Poisson bracket, obviously, to no surprise, it really comes into it really assumes a very significant and a big role for characterizing the lack of integrability and the weakened integrability that appears in the 20 vertex model, and how this relates to the type of information on integrability of inhomogeneous limit shapes and integrability of the Hamiltonian flow that appears in the six vertex model, that is not is not always completely clear at the moment would also exist and hold true for the 20 vertex model. And this is given by the fact that we make use of for computations with a Poisson bracket so that we can study integrability, two types of Poisson brackets. The first Poisson bracket is given by the fact that we can write it as given two test functions f and g, we can write it as an imaginary integral over the compact interval minus L to L contained within the real line, as well as integrating over this difference of derivatives. And these terms psi bar here, just to describe it without actually having to like define everything, because then we would be here all day. But they're just solutions to the nonlinear Schrodinger's equation. So the nonlinear Schrodinger's equation, it relates to this quantum inverse scattering framework because it's ultimately reflecting different types of constraints that we have from the Heisenberg uncertainty principle, which is coming from nonlinearities of the wave function from solutions to the nonlinear Schrodinger's equation. And besides the first Poisson bracket for f and g above, we can also look at a second Poisson bracket, which I like to call the tensor product of the Poisson bracket, because we instead insert a multiplication by the Poisson or by the tensor product instead of the ordinary multiplication. And given two test functions a and b, we can define a very similar type of expression, just instead of using the ordinary multiplication for multiplying the derivatives together that we're taking with respect to the wave function from the solution of the nonlinear Schrodinger's equation, we're instead inserting a multiplication from the tensor product. And this is really helpful because it essentially helps us degenerate taking the tensor product of the Poisson bracket of two transfer matrices, which is an object that we're going to introduce a little bit later, and how really this helps us determine how many Poisson brackets are reflected or present in a Poisson structure for either 2 or 3 dimensions, respectively, for the 6 vertex model and the 20 vertex model. And DiFrancesco's determinantal representation for the 20 vertex partition function comes into play because he looks at inhomogeneous and a homogeneous determinantal representation. And his work is really seminal because it's really highlighting a completely different aspect of the 20 vertex model from the fact that this partition function in this homogeneous determinantal representation on the screen, it's in bijection and it's under a correspondence, and it has a lot of interesting characteristics and connections with the total number of domino tilings. So the matter of the fact is that because the 20 vertex model is defined over the triangular lattice, we can look to make connections between the 6 vertex model and the 20 vertex model from this higher dimensional state space in comparison to the 6 vertex model. And that also allows us to look at and study some combinatorial structures that are kind of maybe a little bit more difficult or esoteric to grasp and to formalize and to conceptualize in the case of the 6 vertex model. And this determinantal representation is given from the fact that it's just given by the fact that it's homogeneous because there's no prefactor appearing in front of the determinant, because as I'll show you on the next slide, there's an inhomogeneous determinantal representation for the 6 vertex partition function, which is also given by another determinant, but there are a bunch of prefactors that are dependent or proportional to the weights of the 6 vertex model that appear right in front of this determinantal representation that can drop out when we take a homogeneous limit and send all the parameters, all the spectral parameters, that is, of the 6 vertex model or even of the 20 vertex model to a common value. It's typically taken to be 0 in the literature, but you can really do whatever common value you want, which would then result in an unstaggered vertex model and, a vertex model in which the inhomogeneities along every degree of freedom about every vertex contained within some finite volume of the 20 vertex model or the 6 vertex model are the same. And this is given, as I had alluded to, the determinantal representation is given by the fact that it's taken as a determinant of a matrix with these entries from between 0 and n minus 1. And it's given by 1 plus u squared or 1 plus 2u minus u squared, as well as being normalized by some non-zero expression. And as we had alluded to in the last slide, the inhomogeneous determinantal representation for the 6 vertex model under domain walls takes the following form, in which, like I had drawn the attention of the viewer to in the light of appearing in this representation. Oh, I'm sorry, my screen froze for a second. But okay, sorry, I'll just repeat what I was saying. So this inhomogeneous determinantal representation is different from the homogeneous one from the fact that there is a prefactor appearing in front of the determinant that is dependent upon the product of weights for the six vertex model, as well as where the determinant of the matrix takes this form. It's C, one of the isotropic weights of the six vertex model by the functions by the weights A and B, which are dependent upon the spectral parameters lambda and nu. And under special assumptions, the six vertex determinantal representation equals the following. So for the 20 vertex model, the determinantal representation can be also analyzed in terms of making some special assumptions on the prefactor for the inhomogeneous determinantal representation, which in this case is given by a product of n factorial squared, two sign factors, because we're looking at sign of the difference of the two spectral parameters, and another factor corresponding to sign of adding the two spectral parameters together raised to the n squared, namely the total number of points in in the restriction of the square lattice from the pentagonal grid. But the determinant, which is appearing in this determinantal representation here, is instead given by a generating function of a partial derivative with respect to lambda of this function, sine of 2 eta, sine of lambda minus eta, and sine of lambda plus nu, sine of lambda or plus of the two spectral parameters lambda and nu. And we can connect the contour integral and determinantal representations by the following identity or proportionality, given by the fact that if we have some smooth enough function f, if we want to say that this function is dependent upon some function omega of epsilon, where omega is also dependent upon some explicit expression that's given in the paper, which coincides with the expression that's given for this function omega for the six vertex model. When we send epsilon sufficiently close to zero, we can represent this function that's dependent upon some sufficiently small parameter epsilon, as well as the weights of the six vertex model, in terms of a contour integral representation where this function h of n of z is a determinant that we're integrating against, as well as the function f of z, which is obtained from before substituting omega of epsilon into f and sending epsilon sufficiently close to zero. And now I just wanted to really briefly introduce the 20 vertex model so that we can establish and really hit home with the types of comparisons that we have been making. And this is given by the fact that for the 20 vertex model, it's defined as having a very similar sample space as what's given for the six vertex model. Only the difference is that we have 10 possible configurations along the top row, as well as 10 possible configurations along the bottom row, which gives 20 configurations instead of 6 configurations in the sample space. And this is given by the fact that depending upon which arrows are either ingoing or outgoing from a vertex, because the ice roll for the 20 vertex model takes the place that either you can have 3 arrows pointing in or 3 arrows pointing out of each vertex from the triangular or the pentagonal grid, whatever you want to call the lattice. This can be given by the fact that you can write the partition function in this way. And as we had alluded to in the case of the six vertex model, there's a way to establish a correspondence between arrow configurations and line configurations. And this is given by the fact that from the line configurations, which we gave for the 20 vertex model in the previous slide, we can have arrow configurations which are used to group different configurations within the sample space of the 20 vertex model, which have the same weight. And we can introduce the 20 vertex model probability measure pretty much in the same way that we did for under domain wall boundary conditions for the six vertex model, in which we're looking at the probability measure supported over the triangular lattice under domain walls C. And under these domain wall boundary conditions, we can formulate a probability measure for the six vertex model as W of 20 V of omega, normalized by the 20 vertex partition function that's supported over the triangular lattice. And there's an explicit expression for the six weights, which appear in the 20 vertex model, which are just given by different types of combinations of the parameters A1, A2, A3, B1, B2, B3, as well as C1, C2, and C3. And as I had alluded to earlier in previous comments, the tensor product of the Poisson bracket of 20 vertex transfer matrices, such as given for the 20 vertex model supported over the triangular lattice, is really taking this form, in which we're looking at taking the tensor product of one product representation for the transfer matrix, as well as looking at another entry being of the product representation that's dependent under different spectral parameters. And from these transfer matrices that are dependent upon different spectral parameters that are not equal, then we can obtain the total number of relations which are given in the Poisson structure. And in the case of the six vertex model, this was coming into play because it really helped us be able to analyze 16 Poisson brackets which appear within the Poisson structure, and being able to deduce that there's some nice action angle coordinates which exist and satisfy the property that the Poisson bracket of the action angle coordinates with its Hermitian conjugate vanish. And we don't exactly have that same property with the 20 vertex model, but we can still make use of the quantum inverse scattering method in the quantum inverse scattering framework for being able to form contour integral and determinantal representations for the for the partition function as well as for the emptiness formation probability. And this is like how I alluded to, this is the product representation for the 20 vertex transfer matrix. And in a previous work that I did on the 20 vertex model earlier this year, I looked at ways to make use of this product representation from L operators that are defined in the literature, and how performing several computations with the L operators can help us obtain a system of expressions for each one of these entries, which appear in this generic product representation for the 20 vertex transfer matrix. An explicit definition of the transfer matrix mapping is given by the fact that we have some complicated mapping, which is given by a tensor product of C3. We're looking at C3 because we're defining the six vertex model over the triangular lattice in 3 dimensions. And this is given by the fact that the other factor of C3, which appears in the pre-image space of this transfer matrix mapping, is given as being raised to the tensor product of the absolute value of n, namely the total number of however many dimensions there is in this object, as well as the L1 norm of M, which is assumed to be a vector in previous arguments in a previous paper that I had given for studying weak integrability of the 20 vertex model. And the image space of this transfer matrix mapping is given by the same space as the pre-image space, in which is explicitly given as a product over J and K from a 3x3 diagonal matrix that multiplies the R matrix. And the particular, or the specific choice of the R matrix that I used for this factor in this transfer matrix mapping is given by the universal R matrix, which it's given and described further explicitly in other presentations I have on the channel. If you go and look for my triangular ice playlist, I talked about a lot of these specific objects that are related to Q exponentials and other combinatorial objects, which are used for looking at a higher dimensional, more general construction of the R matrix that's used for the six vertex model. And for contour integral representations, as we had alluded to also, we had mentioned that we can look at a way to form a proportionality from a contour integral representation for some function f as epsilon is taken sufficiently close to 0. And this is given by the fact that we're integrating against this determinantal representation, which is another determinantal representation that's associated with the inhomogeneous and inhomogeneous determinants that DiFrancesco uses in his work for the 20 vertex model, which have combinatorial implications with with regards to the total number of ways of being able to tile an Aztec diamond. And for the 20 vertex model, the bases of the triangular lattice are denoted with either the up arrow being the first basis of the triangular lattice, the side arrow being the second triangular basis, as well as the down arrow being the final triangular basis. And having this arrow representation for different types of bases of the triangular lattice that we're looking at, it comes into play because we have to form various expectation values, which are used to quantify different aspects of the transfer matrix, as well as various characteristics of the three-dimensional Yang-Baxter algebra, which I'm going to very briefly describe before closing the presentation up. And as we had also alluded to, it's really helpful to be able to think about the 20 vertex model and the 6 vertex models together. And this is given by the fact that the determinantal representation for DiFrancesco's 20 vertex partition function is obtained from U-term boundary conditions of the 6 vertex partition function, in which the partition function of the 6 vertex model from the inhomogeneous determinantal representation under U-term boundary conditions, in which boundaries between neighboring lines of the square lattice are connected together with U-turns. That's what U-turn boundary conditions are for the six vertex model. It's proportional to the determinant of script m prime, where m prime is given as some matrix that's 1 over a product of a and b weights for the six vertex model, as well as being subtracted by 1 minus a product of other a and b weights for the six vertex model. And as we're closing the presentation out, a lot of what's really underlying the quantum inverse scattering framework for the 20 vertex model is the three-dimensional Yang-Baxter algebra, which can be looked as an algebra that's generated from the Poisson bracket of the tensor product of three transfer matrices. So if you just take one transfer matrix that's dependent upon U and another transfer matrix that's dependent upon the spectral parameters U prime, we can also look at a third transfer matrix that's dependent upon the spectral parameters U prime prime, and we can take various Poisson brackets of tensor products of these three transfer matrices to be able to form and study the three-dimensional Yang-Baxter algebra, which is really underlying a lot of features and very favorable qualities of the quantum inverse scattering framework that have many types of implications like what I've been describing throughout the whole presentation. And a lot of these relationships are given like of relationships of these forms. We can pick one operator or one of the block representations for one transfer matrix, and then we can multiply it from the operators which appear in any of the two other transfer matrices, which are dependent upon U prime and U prime prime, which can then help us look at various ways to express these products of operators from the three transfer matrices for the 20 vertex model. And as I had been alluding to, we're able to do all of this because within the quantum inverse scattering method, because we're adapting arguments within the QISM framework from several works, actually not just one work, several of them, due to Pronko, Giulio, and Colombo, in which they're looking at a way to obtain a contour integral and determinantal representation from the bottom partition function of the 20 vertex model from the top partition function of the 20 vertex model. And they introduce this geometric segmentation of space in which they segment the finite volume over the square lattice into the top and the bottom part. And in a way, we can do the same type of thing. We partition the top part of the triangular lattice from the bottom part of the triangular lattice. But for the 20 vertex model, we also have to look at, as I'm saying here, looking at another segmentation along a side in which we look at a side partition function of the 20 vertex model, and then we're using this to obtain a partition function for the other side of the 20 vertex model over the triangular lattice. And in the paper, the final contour integral representation for the emptiness formation probability E of P takes the form below, in which it's obtained from applying a symmetrization of the second contour integral representation that we obtain for the emptiness formation probability. And it's given by a pretty complicated expression, which is given by a nested contour integral of a surface over S1 prime, namely the collection of all surfaces which have a residue at 1, 1, as well as having another collection of contour integrals besides the outer part that are nested over S prime 0, namely the set of surfaces over the triangular lattice which have a residue at 0, 0. And then it's given by a product of several cross terms that are either dependent upon the spectral parameters S or S prime, in which we can look at the product between 1 and J to S, or even 1 to J prime to S prime. And then we also have contributions in this symmetrized contour integral representation of two determinants, capital H n of S, as well as capital H n of S prime, which are given by determinantal representations from the 20 vertex model that I had introduced in an earlier slide that Di Francesco makes use of for establishing several, as we had mentioned, combinatorial implications and characteristics of the partition function for the 20 vertex model. And this expression really actually isn't that hard to obtain because a lot of it is pretty much just a generalization of up to one dimension of this emptiness formation probability for the six vertex model over under 20 or under domain wall boundary conditions. So that's a really great way because it allows us to establish a way in which similar boundary conditions of vertex models would then allow us to establish that maybe there's some other type of similarity between the emptiness formation probability or other types of objects of the quantum inverse scattering method that we haven't previously explored yet. And so the conclusions is that we discussed connections between 6 vertex and 20 vertex models. We highlighted properties of various representations for the partition functions of vertex models. We alluded to similarities in how QISM is used in previous works of the author on the 6-vertex model and the 20-vertex model, and we gave a future description of maybe potential future adaptations of this framework. And thanks so much for watching.